Hello friends, welcome to video lecture on kinematics of machinery. In the today's session, we learn about degrees of freedom, Kurzbach criterion and its applications to plane mechanisms, then Brugler's criterion for plane mechanism. So let us start with the degree of freedom for the plane mechanism. It is defined as the number of input parameters which must be independently controlled in order to bring the mechanism into a useful engineering purpose. So in other words, number of input parameters required to define any mechanism. Okay, so if you just consider the 4-bar chain example, okay, so in this case, if you look to us here, the 4 links with us, link number 1 is here, link number 2 is here, link number 3 is here, and link number 4 is here. Okay, so if I give the input motion for link number 4, okay, so here input motion, here the angle theta made by this link 4 with the horizontal axis with us means this theta is sufficient to define the configuration of the remaining links. Okay, means it possesses a single degree of freedom. Okay, so here already information is given. So in other words, we say that the number of degree of freedom of the 4-bar chain is 1. Now let us consider the case of 4-bar chain. So in this case, the total 5 links with us. Okay. Now look towards this one. Angle made by this link number 5 with the link number 1 or horizontal axis is nothing but the theta 1. At the same time, if you just see the angle made by the link number 2 with the horizontal axis theta 2 is shown here. So whatever the input motion given by us, okay, that is not transferred towards the last one. Means the motion of the last link is independent on the motion of the link number 5. Okay, so it possesses the two different parameters, or it requires the two different motions here. Okay, theta 1 and theta 2. Okay, means it possesses the 2 degrees of freedom. Okay, so clearly mentioned here. In this case, two variables such as theta 1 and theta 2 are required to define completely the relative positions of all the links. Thus, we have that the number of degree of freedom is 2. So, for this, the general actual relationship with us, okay, so that will depends upon the number of links, number of joint, okay, and number of here the higher pairs included in given mechanism. Okay, so that relation we can get with the help of this relation. Okay, this formula n equals to 3 into L minus 1 minus 2j minus h, where this j is nothing but the number of joints, h indicate the higher pairs, L indicate the number of links. Okay, so this equation is known as Kurzbach criterion for the movability of mechanism having plane motion. So in this case, if there is no 2 degree of freedom pairs or higher pairs, then the value for this h becomes 0. If I substitute the value of h as 0 here, then we get this equation in this way: n equals to 3 into L minus 1 minus 2j. So let us see the applications of Kurzbach criterion to plane mechanisms. Okay, for that the different cases in front of you. Okay, so in the previous case already I have seen this formula n equals to 3 into L minus 1 minus 2j minus h. Okay, now can apply this formula for the various cases. Okay, whether or to determine the number of degrees of freedom with respect to all the cases. Let us consider the first case where it includes the 3 links or combination of the 3 links. Okay, so already information with us, the mechanism as shown in figure A has 3 links. Now look towards this mechanism carefully. Just focus here on the first mechanism only. So in this mechanism, the 3 binary joints with us. Binary means when the 2 links are connected at a single point. Okay, that link is known as, that joint is known as binary joint. Okay, so just see in this case how many binary joints with us apart from this one. Okay, just see the number of links. First of all, first link with us, second one with us, and third one with us. Now see, this first link is connected with the second one. Okay, this form the first binary joint. Link 2 with the 3 forms a second binary joint. 3 with the 1, this will form a next binary joint. Okay, so in this way we can get the number of links from this mechanism as 3, as well as the number of binary joints, okay, as a 3. Now if you look towards this relation given, n equals to 3 into L minus 1 minus 2j minus h. Okay, so we'll discuss about this higher pairs in the coming session. Okay, so if you look to us here, 3 will remain as it is. What's about the number of links into this mechanism? So total number of links with us 3. Okay, 3 minus 1, so minus, what's about this one, 2j. So j is nothing but the number of higher pairs, sorry, number of binary pairs, or in another word we can just say the number of lower pairs. Okay, so just count the number of binary. Already we have written here the number of joints with us, 3. So substitute the value for this h as 3, value for the h with us 0 in this case. Okay, so if you look towards this equation, just do the calculation. 3 multiplied by this 3 minus 1 means how much? Here we can get the 6. 6 minus this one 6 is nothing but the 0. Okay, we'll see in the latter part what is the meaning of this 0, 1, 2, okay, etc. Okay. Now just focus on the next mechanism. So in this mechanism, the 4 links with us, 1, 2, 3, 4. Apart from this one, just count the binary joints. So joint number 1 is here. Okay, then next one, second one is here, third one is here, and fourth one is here. So total number of links with us 4, and number of joints with us also 4. Now just substitute the values of this number of links as well as number of joints into this equation to get the movability or degrees of freedom. Okay, so just say if you just see this relation with us, n equals to 3 into L minus 1. In this case, the number of links with us 4. Just replace this L by L term by 4. What's about the number of joints? 4 joints with us. Now do the calculations. N equals to 3 into 4 minus 1 means how much? 3 into 3, 9, minus 4 into 2 is nothing but the 8. Okay, so 9 minus this one 8 is nothing but the 1. Okay, correct. So if you look towards the next case, 5-bar mechanism, just count the number of links, 1, 2, 3, 4, 5. So 5 links with us. Apart from this one, just count the number of joints, 1, 2, 3, 4, 5. So 5 joints with us. Okay, now just substitute the values into this equation. So n equals to 3, number of links with us 5. Okay, again the number of joints with us 5. Okay, so to the calculation, just check the value for the same. Okay, here 5 minus 1 means 4. 4 multiplied by 3, 12. 12 minus this one 10 is nothing but the 2. Okay, so just move towards the next case. Okay, so in this case just count the number of links, 1, 2, 3, 4, 5. Okay, now number of links with us 5. Now just see the number of joints. Okay, for that, if you look towards this one, the joint at point B and joint at point D is nothing but the binary joint, where the 2 links are connected at a single point. Okay, so this becomes a binary joint. So what's about this one? The 3 links are connected at a single point, at point A as well as point C. So this is the case of ternary joint. Okay, so in this mechanism, the 2 binary joint with us and 2 ternary joint with us. So in our previous discussion, already have seen 1 ternary joint is equivalent with the 2 binary joint. Okay, so in this case, the 2 ternary joints with us, 2 ternary joints with us means 2 multiplied by 2, how much? 4. 4 plus this one joint is here. Okay, binary joint with us, and another binary joint is here, means here 4 plus 1 plus 1 means how much? Total 6. 6 equivalent binary joints with us as far as concerned with this case. Okay, so you can get here the number of links with us 5, and apart from this number of joints with us 6. Just substitute the values in given equation. Okay, so here we can get n equals to 3, L with us 5, 5 minus 1 minus 2j, number of joints with us how much? 6. Okay, just substitute here a value and just say 3 multiplied by this one 5 minus 1, 4. 4 multiplied by 3, how much? 12. So 12 minus 12 is nothing but the 0. Okay. So number of degrees of freedom for this case with us is nothing but the 0. Now move towards the next case. Now if you focus on the 6 bar mechanism, so in this case, we look towards this one. Link number 1 is here, 2 is here, 3 is here, 4 1 is here, and link number 5. Entire link between this one B and D indicate the link number 5. So connection between this A and C, okay, is nothing but the entire link. Okay, this is nothing but the link number 6. Don't consider this one half portion separate, this one separate, this one separate. Okay, so no any pin connection is here. This link only overlap with this link. Okay. Now, first of all, just see the number of links, total number of links with the 6, and just count the joints. Okay. So in this case, no any binary joint with us. Don't consider this joint as quaternary joint because only this link is overlap with this link. Link number 5 is overlap with the link number 6. Don't consider this as any joint. Where this one dot shown or pins are available with us, you have to consider that joints only for calculations of number of degrees of freedom. Okay, so in this case, how many joints are there? 1 2 3 4. And if you look towards this actually particular points, so here ternary joints are available with us. Just count the ternary joints. 1 2 3 4. 4 ternary joints with us. So 4 multiplied by 2, automatically how many joints we can get it here? Total number of joints with us 8. Okay, and the number of links with us 6. Now just substitute this data into this relation. Okay, so what do we get? N equals to, here clearly written, n equals to 3 into 6 minus 1. 6 means here number of links with us 6 minus 1 minus 2 multiplied by 8. So what's about this 8? 8 is nothing but here. So after conversion of that ternary joints into binary joint, we can get the number of joints equals to 8. So do the calculations. Here what we get? N equals to minus 1. Now see the meaning of this one: 0, 1, 2, minus 1, etc. Okay, this will clear to you the next slide. So it may be noted that when n equals to 0, then the mechanism forms a structure or no any relative motion between the links is possible. If you look towards this one, case number, this one A as well as case number D. So for these two cases, we have found the value for n equals to 0. This case also 0 and in this case also 0. So this form a structure, no any relative motion between the various members, okay, will take place. Now, when n equals to 1, then the mechanism can be driven by single input motion, okay, as shown in figure B. So already we have seen here input motion. Okay, if I give the input motion for this one, that is sufficient. Okay, so already that part we have seen with the help of okay, so this one, whenever actually input single input motion is given for this one, okay, this is sufficient for us. Okay, means this carries only single degree of freedom or movability equals to 1 for this case. Okay, now when the two input motions, separate input motions are required, okay, so here we can require one input motion in between this link number 1 and link number 5. Similarly, can require the another input motion here. Okay, so can get the we required the two separate input motion for this one. Okay, then when n equals to minus 1 or less, then then there are redundant constraints the chain, and it forms a statically indeterminate structure. Okay, whenever the value for n is less than 1, then that form a statically indeterminate structure. Now say some of the applications of the Putzpatch criterion to the higher pair. Okay, so in this case, if you look towards this one, this example in front of you, apart from this, the second example in front of you. Okay, now see here, there are the three links. Okay, in case number 1, there are the three links. Okay, so at this spot, this one and this one, link number 1 with link number 2 as well as 3. Okay, at this point form two binary joints. Okay, so apart from this one higher pair with us. Now see this one, already I have seen the meaning for the higher pair and lower pair. So what's about the lower pair? When there is the surface contact is there, okay, in between the two links when there is the relative motion takes place. So in this case, even though this looks like a point, but these are nothing but the pin connections, okay. So here actually surface contacts, and here is nothing but the point contact, okay. So point contact in between the link number 2 and 3, so this form a higher pair. So if you just see the formula available with us, okay, same formula we have written here, n equals to 3 into L minus 1 minus here 2j minus this one, this formula 2j minus h. Now if you look towards this case, here in this case the three links with us, number of joints with us, number of joints, number of joints with us, binary joints with us 2, and here the number of actually higher pair with us 1. So in this formula just substitute the values. So n equals to 3 into n equals to 3 into 3 minus 1. Okay, why 3 minus 1? Because number of links with us 3. Minus 2 into 2. So what's about this 2 indicate? Number of joints. Okay, and minus 1, this indicate the higher pair. Okay, so do the calculations, check the value for the n. After doing calculation, we get the value for n as 1. Means single input motion is sufficient to define such type of the mechanism. So what's about the next one? So in this mechanism, there are the 4 links. So what's about that 4 links? Now, link number 1 is here, okay, link number 2 is here, link number 3 is here, and link number 4 is nothing but the wheel. Okay, so first of all just see the number of links. Okay, number of links already with us 4, and number of joints. Number of joints, here the binary joint form between this link number 1 and 2. Okay, first one is here, then link number 2 form a binary joint with the link number 3. Okay, similarly link number 3 with the 4, that will form next binary joint, and link number 4 with the 1, that will form here higher pair. Okay, so remember that here we can get the point contact between this link number 1 and link number 4. Okay, so that actually motion includes the partly sliding and partly turning motion. Okay, so just try to solve this relation. Okay, what do we get here? N equals to 3 into 3 minus 1, sorry, 3 into L minus 1. So L with us, number of links with us 4, just substitute here, minus number of joints with us 1, 2, 3. Okay, 3 binary joints and 1 higher pair. Okay, so here you can get the value for the n after calculation equals to 2. Now see the Grubler's criterion for the plane mechanism. So the Grubler's criterion applies to the mechanism with only single degree of freedom joints, where the overall movability of the mechanism is unity. Now substituting the value of n equals to 1 and h equals to 0 in Kurzbach equation. Okay, so Kurzbach this equation with us. Okay, this actually applicable to only when the degrees of freedom equals to 1, means here we can just substitute the value for n as 1 and h equals to 0. Okay, so what we get here? We can get this 3 into L minus 1 minus 2j equals to 0, sorry, equals to 1. Just here you can get this relation like this one. Okay, so just modify this relation by multiplying this 3 term to inside terms. Okay, what we get here? 3 into L minus 3 minus 2j. So in this way you can get this relation. Okay, so we can get 3L minus 2j minus 4 equals to 0. So this equation is known as the Grubler's criterion for the plane mechanisms with the constant motion. So here one more actually important point is given. A little consideration will shows that a plane mechanism with the movability of 1 and only single degree of freedom joints cannot have an odd number of links. The simplest possible mechanisms of this type are 4-bar mechanism and a slider crank mechanism in which L equals to 4 and J equals to 4. Thank you. Hope in the today's lecture whatever the points we have covered, okay, clear to you.